So today we're going to do the third installation of everything I forgot from stats class. So we're going to go over data visualization, the why, what, and how. Okay, so just background concepts and definitions. So probability distributions are going to be really important for this discussion. It describes the probability of outcomes for random events. So for example, for this chart, you've got two probability distributions, one for females and one for males. And the random event is going to be that, for example, on the left chart, that a female gets measured her height. And the outcome is going to be that specific height, and the probability is going to be on the y-axis. So, for example, an outcome of being 5'4" for a female, the probability is about 17% in this. All right, so normal distributions are going to be the most important probability distributions, probably for statistics. Common examples are going to be IQ, height, CDC, anthropometric statistics, z-scores, for example, like BMI z-scores, height z-scores. Those are all kind of standardized in order to hopefully meet a normal distribution. In actuality, nothing's ever completely a normal distribution, but some of them can be, kind of close, kind of approach it, be good enough to be normal to be able to use parametric statistics for those. And so those are what you use whenever you have presumably a normal distribution. You're comparing, for example, two mean values. If you wanted to compare the males and females' heights, you would use a t-test. And you'd use an ANOVA if you had three categorical levels for a variable. Continuous non-normally distributed variables would be like things like salary, length of stay. For those, you would use non-parametric statistics. All right, so this is the normal distribution function. So the probability distribution density function is that thing that's on the very top right, and that's a very specific mathematical definition for what describes this curve. And so, of course, in reality, like I said, nothing ever is exactly a normally distributed function because, that's a very precise definition, but things can approach it. And so whenever they're close enough, it's really just kind of like you're making a judgment. Is it close enough to a normally distributed function to count to be able to use a parametric statistic? So with this, you've got mean, median, and mode all lining up in a normal distribution function. So all of those are equal to mu. And then standard deviation is equal to sigma. And so that's a very important property of normal distributions, is that the mean, median, and mode all line up. So the mode is going to be the peak of the hill. The median, you can see that it's equal to the middle because it's completely symmetric, and the mean is lining up with all of both of those. So whenever you're looking at a probability distribution function, and you take the area under the curve from one point onward, then you're getting the probability that something's greater than some other value. So if you're looking at this, you look at the dark blue for 2 standard deviations or above, it's going to be like that 2.1% plus 0.1% for greater than 3 standard deviations. And so that's the probability that something's greater than 2 standard deviations above. And you can use those calculus formulas below to integrate, to figure out the area under the curve. And so for a two-tailed test, you have something that's greater than or less than, positive or negative 1.96 standard deviations respectively. And so for example, if you've got 1 plus or minus 1 standard deviation, about 68% of the sample should fall within 1 standard deviation of that mean value. Okay, you can also have probability distributions for categorical variables. The most common one that we usually use and think about is going to be a binomial distribution. So flipping a coin, answering yes or no on a yes or no question, survival or not, things like that are all dichotomous binomial binary variables. So for those, you can use inferential analyses like chi-square test of independence, logistic regression. Other categorical variables can be ordinal. That's not really a probability distribution function necessarily, but it's a type of variable that you can use, and a Likert scale is one of those. So an ordinal variable is just something that's got different categories, you know, numerically ordered as far as integers from like 1 to 5, 1 to 10, whatever it may be, and that a value that they're ordered by some variable, like ordered in some manner. Tossing a die is going to be a multinomial distribution because there's all these different categorical ones that, but it's not necessarily ordered in any meaningful way. Logistic regression models exist for both ordinal and nominal outcomes with greater than 3 levels. So these are ones that aren't necessarily as commonly known, but I use the one for ordinal variables quite a bit. Whenever I've got really skewed data, I may transform it, may take the quartiles of something, and then do this logistic regression with a cumulative odds model to analyze that. Okay, so one thing that gets in the way of something being normally distributed is that if it's skewed. So skewness basically means that it's an asymmetrical distribution. The problem with that is that it's not normally distributed. So you can see there on the right, you've got 2 examples. One is negatively skewed, the other is positively skewed. So examples of things that are positively skewed are going to be things like salary and length of stay. So most of us fall somewhere within, you know, the bulk of that hill there. Most of us have, you know, modest salaries, but some people are billionaires and they're going to be extreme outliers on the right. And so that's what a positively skewed distribution looks like. If you look at the bottom there, you can see, like I said earlier, with the normal distribution, that's going to be the one in the middle. The mean, median, and mode all line up, but with positively skewed ones, you can see that they all don't line up, and they're doing so in a meaningful fashion. So because of those extreme outliers, the mean is going to be more effective than the median or mode by those. The mode, again, aligns up with the hill, whereas the with the peak of the hill, whereas the median is going to be less influenced by extreme outliers because you're just looking at the 50th percentile. So the most extreme values can be as high as they can be, and it won't really affect the median value at all. And then you see the inverse patterns for the negative skew. The solutions for those could be to transform the data. There's a lot of different transformations. We're not going to really get into examples of those, but you know, you can do like a logistic transformation. You can take the square root. There's various ones you can do to try to make them more normally distributed. You know, of course, the problem with that is that it's less meaningful. You don't necessarily know what an increase in you know, the square root of income means as much as you do with just looking at the raw data. Another approach is to use non-parametric statistical approaches. And so those are useful as well for that. Outliers are another problem. So a value that differs substantially from the other values on a variable. So in some cases, those may be erroneous. For example, if you're looking at height and somebody measured it in centimeters instead of inches, then that would be an error. And you kind of want to check these outliers to make sure that there's no error or there's no problem whenever it was input. They may still be accurate, but they're going to still affect your inference potentially. So if you look at the guys on the right there, that's like a classroom and they're all the same age, but one kid is huge compared to the others. So if you took the mean height in that, it would very much be influenced by that kid. And so if you were to run statistical analyses, that kid would, you know, would mess up all the analyses and it wouldn't necessarily be representative of the typical class. So you can either remove that kid from the sample or you can trim the data. You know, you can say, we're going to just, anybody that's higher than a certain point, we're going to cut it down and say that person is just going to be the other maximum value, or, you know, you can take the 95% confidence interval for the group and cut them down to that point. So there's ways of doing that. Another way, again, is you can do a transformation of height to make it more normally distributed. All right, so data visualization. So the purposes include examining univariate distributions. So you can compare the distributions with the assumed probability distribution in most cases, you're asking the question, is this data approximately normally distributed? And that's going to tell you whether or not you're going to use parametric stats or other stats, or whether you need to transform the data. You can explore relationships between variables. So again, if you've got two variables, probably the most common one is going to be correlations, you know, just as a kind of statistic to see that. And if you use correlations or something, you can explore that through a scatter plot to see whether or not that's meaningful. You can verify test assumptions, for example, homoscedasticity and linear regression. I'm not going to get into that necessarily. And you can communicate results to an audience. All right, so univariate analyses. As far as univariate variables, my favorite is the Boxplot because it gives all the most important descriptive statistics, and it also visually shows the distribution, so you can get an idea of how normally distributed something is just based on looking at it. So the box in the middle there gives you most of the important statistics that you'll need. It's got the median, which is the middle horizontal line. Sometimes it'll have the mean value represented as like a star, an asterisk, or a circle. In this case, it's an X. I've got Q1 and Q3 in the interquartile range as well. So those are important. Interquartile range, anything within the box is going to be about half of the data points within a box and whisker plot. The rest of them are going to be outside, with either within the whiskers or within the outliers. So, and you can, I'll explain this later, but you can use the proportions of the various lines to determine how normal something is. So the whiskers are going to be the vertical lines, and they're at most 1.5 times the interquartile range. And so that's a bit of, I think, an arbitrary cutoff, but what they've used is that if it's 1.5 greater than the box, then it's going to be something's going to be considered an outlier. If there's no value that's as high, if the maximum value, for example, is at 1.5 times the interquartile range above Q3, then the horizontal line at the end of the whisker is going to just be whatever that maximum value is. Outliers are going to be things that are more extreme than the box, plus or minus 1.5 times the interquartile range. And so again, that's kind of arbitrary, but it's still very useful, as it turns out, whenever you're looking at trying to identify outliers on a plot. The other option that's very commonly used is histograms. So what you do is that on the x-axis, you've categorized the continuous variable, in this case, mileage, miles per gallon. That's something that's a continuous variable. It can be any number between 0 and however much. You've grouped that into different levels. So here we've binned those between, for example, what looks to be 30 and like 34 or something like that, are all kind of binned together within that, and we're just plotting the frequency of all patients or all people or all miles per gallon that fall within that range. And so that's what you do with a histogram. On this, what the kernel curve is representing is what is essentially a representation of what that would look like if you had a large enough sample, and if you didn't bin at all with regards, didn't use a bin at all with regards to the miles per gallon. So if you were to draw a horizontal line for every single mile per gallon that's continuously done, you know, and then you drew that up, that's what the frequency would generally look like, what that curve would be. And so you can compare that to the normal distribution, which is just using the mean and standard deviation based on what you've got for that variable, the miles per gallon. And you can see that it's not quite normally distributed. The kernel and the normal don't overlap. You can also see that it's kind of skewed anyway. And so you can see that the miles per gallon is probably not necessarily normally distributed. All right, so what I've done here is that I've created a normal distribution with some random error that's supposed to have a mean of 0 and a standard deviation of 1. And then I've created a positively skewed one and then a negatively skewed one based on that, doing a transformation of those that are supposed to have positive and -1 skewness, respectively. And so I've tabulated the descriptive statistics there in the top left. So based on that, it's hard to kind of look at it and see how normally distributed it is. You can definitely look at the skewness statistic, which is going to be important, but like I said, it's really a matter of judgment whether or not something's close enough to being normally distributed in order to be able to use it in parametric statistical analysis, or whether you need to transform it or do cutoffs and use, you know, categorical, do it as a categorical variable or what. So I've done these different plots. On the bottom left, I've done a box plot. And so the green one is the normal one. And you can see a number of things. You can see that it's pretty symmetric. The mean and medians line up really well. And there's not very many outliers. There's only one, in fact. But if you look at the negative skew, you see something very different, that first of all, the mean is lower than the median, which is what we expected from that previous slide. You can see that the upper whisker is much shorter than the lower whisker, and you've got a whole lot of outliers on the bottom there. You can see that the Q1 or Q3 is fairly close to the median, but the median's a little bit further away from Q1. And so all those things tell you that it's skewed, that it's negatively skewed. In fact, it's not normally distributed. And the exact opposite set of patterns exist for the positive skewed variable. All right, so on the right there, what I've done is I've created histograms for those 3 sets of variables. So that's the same set of variables graphed both ways. And you can see the patterns there. I've done a bin where you've got 25 bins for each of the 3 sets of variables. So you can see that the right ones, or the top one's going to be negatively skewed. There's a big, you know, there's a lot of outliers on the left, and there's bunched up towards the right. The one in the middle is pretty normally distributed. It looks kind of like a bell curve. And the one on the bottom, you know, the opposite of the negative skew, is bunched up on the left, and you've got a bunch of extreme outliers on the right. So various bivariate analyses. If you're looking at 2 continuous variables, the most common one that you're going to want to use is going to be a scatterplot. So here I created 2 random variables and graphed them. And you can see it's just a jumble of points. There's no pattern whatsoever. There's no correlation at all. And you can see that R, the correlation, is approximately equal to 0. And so the regression line that you're going to do between those 2 variables indicates that it's like a horizontal line graphed at the middle of the mean value of the y-axis. And so basically all this to say there's no relationship between these variables, and the correlation says it's 0. But these are 3 examples of correlations that also equal 0. But you can see for each of these are very much, there is very much a relationship between them. It's just not captured by that correlation equals 0. So for each of these, I've graphed these different functions and added a little bit of random error to them. And so for the middle one, particularly, is important. So you can see the correlation is equal to 0. The regression line is going to be, again, the median line there, or mean line there. But if you really wanted to do a regression, you would want to do a quadratic variable or a quadratic predictor. So you would probably have an x² term in your regression formula. And so that's something that wouldn't be apparent if you were just looking at the descriptive statistics in the correlation matrix, for example. But you would find a very strong relationship if you dug into it by looking at the, you know, data visualization through using a scatter plot, for example. All right, and then you can also do data visualization for categorical variables. So for this, I've looked at my pediatric research program, so the students who were at Cook Children's and UNT over the years. And I've got the number of students who presented and didn't present at Research Appreciation Days, doing a poster at Research Appreciation Day. So the first one is going to be not too interesting because all I've done is graph the total number of students who went through Cook Children's and then went through UNT as well. And so that's not super informative. You know, you could basically just present that in a sentence and it would tell you as much information. The right one's a little bit better because while it still gives the total number of students, it also uses the shading, this, you know, stacked column chart to indicate how many students presented and how many didn't. And so that's a little bit better. And I've even done the percentage who presented in there as well. For the next one, I've done the same thing, but I stratified it by the year. And so this one gives even more information, and this is where it's actually starting to get useful to use a chart because this is a lot of detailed information here. So you can start to see patterns that you wouldn't have been able to see if you were just looking, maybe even if you're just looking at the raw data or the tabulated data. So you can see that Cook Children's had approximately the same number of students each year, whereas UNT had this kind of great growth in the number of students they were taking on in the program each year. But you can also look at the percentage who presented. With Cook Children's, you can start to recognize that it's getting kind of better each year. More larger percentage of students are presenting, whereas at UNT, the picture is a little bit more complicated. There's a drop in the number of proportion of students who are presenting in 2019. The right graph is pretty much the same thing. It's called a 100% stacked column chart. And it's all the same information. It just doesn't tell you how many students it was each year, but it's a good way to get a greater look at what proportion are presenting each year if that's what you're most interested in. I'm going to show you how to make all these graphs at the end of this. All right, so ggplot2 and R is my favorite graphing program. I think it's the most powerful program out there, arguably, for graphing, and so I use it a lot, and it does a whole lot of stuff that you can't use in Excel. So this first one is a combination of the Scatterplot and the Boxplots. So you've got two variables, pain before an intervention and pain after the intervention. So first of all, let's look at the Scatterplot. So one thing that's kind of nice here is that you can see that the various pain scores from 0 to 10 are ordinal variables, meaning that there's no like 5.5, there's no decimals at all. So everything's going to be on one of those integers. And so if you've got a whole lot of patients who are all fitting into one dot, like one position on this graph, then they would overlap. But what I've done to counter that is something you can do in R much more easily than you can do in Excel, is that I've created some random error for each of these. So even though, you know, for example, if you look at 6 across and 0 up, you can see that there's a whole lot of patients there, but that wouldn't necessarily be apparent if you were just looking at this without the random error added. So that's one nice thing about using Scatterplots via R. And then of course I've got the Boxplots. And so with the top graph with the pain before the intervention, you can see that before the intervention, it's pretty normally distributed. It's kind of all over the place. After the intervention, they got a lot better, and that's apparent because there's this highly skewed negative or positively skewed variable that's got this big cluster of patients. Most of the patients are going to have pain scores near 0 after the intervention, and so it's just kind of nice to be able to see to fit in a little bit more information in that chart. All right, and so this is kind of an inverse of that. So here the focus is going to be on the bar charts, the distribution, but what's nice is that I was able to actually graph every single data point on it, so it's a little bit more information than your standard box and whisker plot. And you can identify patterns that you might not otherwise see. And it's a little bit better for data transparency as well whenever you're submitting it to a journal or something. With this one of the observations that was really important for the study is that if you look at the right chart, that there's this cluster of data points that were close to 0. And so that was something that was particularly interesting for the study, and it's not something that's going to show up if you're just looking at the box plot or even the descriptive statistics as well. All right, so this is an even more complicated chart. So here what I've done is that I've got 4 scatter plots for 4 different sets of variables, pairs of variables. And I've also got 2 predictor variables that use color and shape to signify what the scatter plot, point is. And so what's useful about that is you can examine it and see, patients who are fitting in with some certain, quadrant of the graph or like a certain area of it. You can see what's going on with those patients. If there's like a cluster of patients who have the same profile as far as those 2 predictor variables. You can also look at extreme outliers and see what's going on with them. Why might they be so extreme as far as outliers? So that top left one's got a very extreme outlier, a multivariate outlier, in fact. And so another thing that I've done that I added to this is that it's got a 95% confidence interval, confidence ellipse, which gives you the gist of it. That oval shape gives you the gist of what's going on, the relationship between those 2 variables. Okay, and then this is one that I really like. It's kind of a timeline of 3 patients. So it's got from the time that they were diagnosed with cancer all the way up until either their last visit that's recorded or the time of death. And it's got the treatment along that way. And so it gives a very detailed timeline that's, expresses a lot of information within just a graph. And I like this one because, for one thing, I think I invented it. I don't know that I've seen it in journals before, but I think it's really, really cool and really informative. And so I've started to use that a lot whenever I do a case series. Okay. All right, so I'm going to go ahead and go to the part where I do a little Excel demonstration. Okay. So what I've done here is that I've got some of the variables that we looked at in the demonstrations and in the presentation, and I've got some graphs here that I'm going to recreate. So the first one is going to be the box and whisker plot. So to create that, I'm going to highlight all of the patients that are for those 2. All right, and I'm going to say insert. Okay, insert recommended charts, and then all charts, and box and whisker. And so this is actually something that's relatively new to Excel. I think that we've only had it at Cook Children's maybe sometime in the last year. We weren't able to use box and whisker plots for Excel until pretty recently. All right, so I'm going to try to make it look like the other one. So it's graphed those 2. But it looks quite different than this. So I'm going to, do the different things to make it match up. Okay. So first of all, I'm going to change the color. So I'm going to right-click this one and say we're going to do a green fill. And then we're going to do a black outline. Okay, and for this one, we're going to do the blue fill. Black outline. And so I don't want the chart necessarily for this one. You may want that, but for this one, I didn't do that. So, and then I'm going to delete these horizontal lines. I usually do that. Most publications don't seem to want to have those horizontal lines. And also, this isn't one that's an essay for this. It's not really a meaningful one, the horizontal axis title. Okay, and then to make this one, this vertical axis a solid line, which again is something that's usually done in publications. I'm just going to make the solid line there as the outline. I'm also going to make an outline around the entire graph. Okay, so that looks pretty good. I think the only thing that we're missing is going to be the legend. So let's see. Okay. All right, so I've created the chart legend, and so I think that's everything to match it up. All right, so next I'm just going to use this normal distribution that we used in the presentation. So again, I'm going to just go over here and do Control-Alt-Down just to highlight all of the variables, all the values. So here, recommended charts, and then all charts again. And then histogram. All right, so this. Move this over. So for this one, you know, this isn't super helpful. The way that they've done it is that they've, you know, broken it up, as I said, in their bins and, you know, very complicated or very long decimals, and so it's not really helpful to see all that. So I'm going to delete that. Usually you're going to want to keep the frequencies here, but I'm going to just delete that to be consistent with the other one. And so for this, we're going to go over there and do, so we're going to say format data series. And then, well, let's go ahead and do a solid fill of green, order, solid line. Okay. Then let's see. Okay. I think I might have chosen the wrong one. Let's see. Okay, I'll come back to this one. I'm going to do the normal distribution one. This is the one that I kind of manually created from it. So what I've done is I've categorized them into these different integer intervals by using these different formulas to kind of compute what they are. So I'm going to just do this, insert, and then recommended charts, and then a clustered column chart. So this is appropriate for what we're looking at. Okay. All right. Okay, so again, we're just going to do that, delete that. I'm going to rename this normal distribution. Okay, and I'm going to first of all change the font for all of it because they make it the you know, standard one is that they make everything gray, so I prefer to use black font. Right click this, make it an outline. Make this an outline. Okay, we're going to make data labels so that it's got the thing at the top of it, the numbers. So add data label. I'm going to, you know, again, change the color to green, black outline. And next I'm going to make it to where it's got, that it's got no gap between them. Okay. Okay. Yeah. So, and let's see, we're going to make a 0 gap between them. All right. And then the next one is just going to be a scatter plot that's got the distribution between them. And so like I mentioned earlier, it's something I created this function using a transformation of one of the variables. So you can see that's why there's this perfect relationship between the two of them. All right, so insert, then recommended charts, and I'm going to use Scatterplots. Okay, so I did from -3 to 3, and I did from -4 to 4. So I'm going to change the axes levels to where the minimum and maximum values for that. So I did -3 on the x-axis, 3, and then I did 4 to 4. Okay, and then again, I usually delete these vertical and horizontal axis lines markers. And then I'm going to change the points so that they're a little bit easier to see. I'm going to make it to where there's no fill, but that it's a black outline over there. All right, so we have to go through this way to do it. So what it was doing is creating a line. We do want 0 line, or no line, but we want the markers still there. All right, so there's circles, no fill, and then solid line is black. Okay, and I think it's probably a little bit smaller, so we're going to say probably a size 2 or 3. Yeah, so that looks about right. Make it a little bit smaller so you can see all the different points there. And then the last thing I think is that we want to have the axis titles. Okay. This is normal. Okay. Okay. And then again, I just like to have the black font for everything. But okay. And so that's how you would do those. All right, so I'm going to go to the column chart. And so let's see. So first of all, so this is what we're looking at. It's the final objective. So I'm going to create column chart for that. Okay. And we're going to use, this is the one that so this is one that's an option, but it's not really as appropriate for this because there's so many different levels of it that it'd be kind of confusing. So I'm going to use this stacked column chart. Okay, so you can see that it's kind of like it, except that it doesn't have these labels that we have here as far as category and the presentation. So, and I haven't figured out a better way to do this, but it seems to work every single time. So I say select data, and then for the horizontal, I'm going to say, let's select all of this so it keeps those column header names. Okay, and then whenever you do that, you can see that it's created this year category presentation one at the very left, which we don't want. So again, you say edit, and this time we're going to just capture this part again, which was the original formulation, but for some reason doing all that, it tricks it into knowing what to do correctly, and it doesn't have, it has it how it's supposed to be. Okay, and so I'm going to resize it to be the right size. So I'm going to go over here and say size, 6.5, the appropriate width. And then, you can do all the things like I was doing earlier. You delete this. Oops. You delete these lines. I'm going to make the font black. I'm going to make the outlines for this. And I'm not going to go through and do all the different colors and stuff, but I just give you some examples of how you might do it. So for this bottom one, it's going to be this dark green. And so you're going to say fill dark green. And just by right-clicking it, you can say do that and do the outline. Okay, for the second one, I'm going to do it the same thing, but I'm going to do the using the legend. That's another option. So I just click on somewhat agree, right click it, outline, and then I'm going to make it this lighter green color. And so you could just go along and do the same with these other ones as well. Okay. The other thing is that we're missing the percentages. All right. So we're looking for the percentages that are strongly agree for each of these. So what I'm going to do is say equals to strongly agree divided by the sum of the rest. Okay. So that tells you the percentage of them that are strongly disagree, or strongly agree rather. All right, so you write, or you click this, you say that we want to have, oops. You click one of these and say that you want to have data labels. You click on one of these labels now, and now you're able to edit it. So we want to get our values from the cell. We don't want one that they've got already. So I'm going to highlight all these. Okay. And so that's the one that we want. And so now I'm going to uncheck the ones that they already had by default that we don't really want. So I'm going to uncheck value. I'm going to uncheck show header lines. So now you've got the percentages, and that's good. That's what you're wanting. The last thing is that it's kind of nice to have it a little bit wider so that the lines of the bar charts don't overlap with the percentages. So I'm going to make this, we'll try 50% gap width. And so it's a little bit better to look at. There's no overlap there. And very quickly show you how you would replicate this. So you can copy and paste a chart. And then, so basically this is just an exact duplicate of the original chart, but we want it to be that 100% stacked column chart. So I'm going to right click it and say change chart type. And then I'm going to go over here and pick the one that we're wanting, this 100% stacked column chart. Okay. And for this one, I chose not to use the percentages because they're all percentages is what we're looking at for this one. So just delete that. All right. And so that is it for the presentation. Okay, did anybody have any questions?
Tyler, I have a question. First, great presentation, by the way, very informative. But something I constantly find myself asking as I'm cleaning data specifically is what cleaning technique do I start with, especially if I don't have a normal distribution. Do I start with a transformation? Do I start just straight with non-parametrics? Do I look for extreme outliers and start trimming them? So I sort of wanted to hear what recommendations you had for when you're cleaning your data. What do you typically do first? And obviously it depends probably, but what are some recommendations you have?
All right, so that's a good question. So what I would do personally is I would look at the box and whisker plot and see what it is that's messing up your data. If it's like one extreme outlier, I'd say go there, you know, trim the outlier, figure out if it's a problem, and maybe that'll fix your whole problem. If it's just this completely skewed data, I might consider transforming it. That's not something that in practice I use that often. I might use a non-parametric analysis, especially if you're looking at a smaller sample size. If you're looking at a larger sample size, I found that transforming it into something ordinal, for example, using the quartiles of some distribution, or using meaningful cutoffs for a distribution, and then using ordinal logistic regression is actually a very powerful technique. And that way you can use all the power of a regular regression technique, but you're able to get, you know, good analyses from that and provide meaningful results as well.
Thank you.
Mm-hmm. Any other questions?
I do. Oh, well, maybe a comment. When multiple times we think we have, you know, good data to do our parametric, and then, you know, find out we're going to do non-parametric. I have in the past transformed only to find out from the reviewers, because I'm talking about when I submit a manuscript on the actual data analysis, that for their readers, they would rather we explain the level of data and do the appropriate non-parametric. You know, that started off, we could have done t-test, but we went to Mann-Whitney U or something, you know, and explain that. And I have seen that multiple times with our nursing research studies in the journals.
Yeah, that's a really good point. You know, it's something they teach you so early on, is to transform your data. And then it seems like whenever you're actually using it in practice, you don't really do that much. One thing that I've found, another point on that, is that if you've got non-normally distributed predictor variables that are maybe covariates and aren't so important, it's probably okay to transform them, because you don't really, you know, care about these other, you know, predictor variables that are just kind of covariates anyway. But if it's a main variable of interest, maybe don't transform it as readily.